My co-author is Ant Siegthorpe, and I'm going to discuss 3 types of GPS satellite that are coming down the pipe, starting with the first one. The first one is called Navigation Technology Satellite 3, or NTS3. It's an experimental GPS satellite. It's, as the name suggests, the 3rd experimental GPS satellite. Number 2 flew nearly 50 years ago. So it's a momentous occasion. It's a mission run by the Air Force Research Lab. And it aims to test and demonstrate capability for resilience and autonomy. The launch is planned to be sometime between November this year and January 2025. It will be flying in geosynchronous orbit, actually slightly below geosynchronous, so it will be drifting around the globe. And it has a phase array. You see here the phase array antenna surrounding the spacecraft. JPL will be delivering the Scion payload. It's a GNSS receiver. The antenna of this receiver is situated at the, it's not working very well, at the center of the spacecraft. The receiver will have the RTGX software from JPL for autonomous orbit determination, and sub-time filter software from the neighbor research laboratory. And we'll also be performing the operational ground orbit determination for this mission. So there will be many firsts enabled by NTS3 Scion payload. It will be the first GNSS receiver co-located with a transmitter. That is a formidable challenge. I will not sort of focus on this capability. I'm going to focus on other things. Just mention that it will do autonomous precision orbit determination in place. It will be the first weak signal GNSS receiver, that is receiver capable of receiving the weak silos of GNSS spacecraft from a variety of frequency and constellation beside L1CA. And it probably will have the highest gain GNSS antenna ever flown in Earth orbit. This is the antenna. It's designed to maximize the gain around the Earth. So there's no particular space geodetic science value in NTS3 mission. So you need not care about it except for one little thing. Then first of all, I'll tell you why you don't need to care about that. NTS3 will transmit GPS signal. It's a normal GPS signal, but it's a high PRN. PRN will be 34. It will be set. It will be not present in the almanac, so the almanac will not tell you about PRN 34, and it will be set unhealthy in its navigation message, and there will be no nanus. So hopefully it will be a ghost spacecraft for you, but that's the one thing you need to watch out for. The spacecraft design itself is not conducive for precision orbit determination. The bus is an S-ring, it's a ring that's designed to have payload attached to it. It's not designed for precision PNT application. It has a massive phase array antenna and fairly irregular shapes. It has a bizarre attitude model or approach. So not anything that you are familiar with GPS spacecraft, and it's an experimental mission. So it's subject to maneuvers and all sorts of things. So it's not going to be well modeled. It cannot be well modeled. Now we will collect the ground tracking data in order to do our orbit determination as our duty is for this mission. And we will remove PRN 34 from the tracking data, and we'll be disseminating the data as we usually do to the various data centers. So we will take measure to make sure that you don't get potentially confusing PRN 34 in your RINEX file. So I do not expect that your receivers will be providing PRN 34 data, but this is something you need to watch. if you're processing data, and we will let you know when the satellite is about to be launched, and when we think the first navigation signal will be transmitted, to watch out to verify that indeed you don't see PRI-34. The next satellite that is going to be launched is GPS IIIF, sometime between 2026 and 2027. And a problem with that, it will carry a high-gain antenna. Now, you heard this morning about the need to model such antenna, and that's a good thing, and you can model it if the antenna is fixed. The antenna of the GPS IIIF is not fixed. It's an articulated antenna. It can point anywhere on Earth. And as you know, when you fly in MEO, the range of pointing could be plus and minus 7 degrees or so to point anywhere on Earth. So this antenna is pointing in this range. And the antenna is roughly, the antenna is on the plus X size of the spacecraft as defined by Lockheed Martin. I think this is the same convention as the IGS. So it will be often shadowed by the sun, but there are orbital geometries where the antenna will be fully lit. The backside of the antenna will be fully lit. So the geometry will be variable, and the key concern here is that the pointing will be unknowable to the civilian community. Only the operators would know where the antenna is pointing. And here, that's the challenge for us. So we're trying to assess what the impact of not knowing where the antenna is pointing. And so, first of all, we try to figure out what happens if you don't know about the antenna at all. What if you assume there's no antenna and there's such an antenna, roughly with the same size, it's about 4 meters square, parabolic antenna. And so we did a simulation where we modeled the spacecraft with and without this antenna. And what you see here are the acceleration due to the antenna alone. This is the antenna, pointing at no pitch and no roll, so it's a nominal location. And the acceleration as a function of the Earth spacecraft sun angle, we call it Earth probe sun angle, is substantial. It can reach nanometer per second square. Another thing that we did is to try to see, okay, suppose you do have some kind of a baseline model for the antenna, but you don't know where it's pointing. And it turns out that a certain pointing angle, particularly in the roll, where the impact, as you see, is the highlighted number, has a substantial impact in the along track acceleration. And along track acceleration is an important acceleration, as you know. And so, and these are the result of that mismodeling. So if you model, you have a model for the an average antenna pointing, but you mismodel the roll, you get propagation error that can reach tens of meters over several days, and over one day they reach decimeter level. So for prediction, this is going to pose a challenge. But it's also a challenge for over-determination. But this is very harder to measure because everyone is doing over-determination a little bit differently. So what we did is we modeled the acceleration error due to the pointing of the antenna, and we inserted it into the JPL standard over-determination process. And on the left, you see the orbital error of the satellite that we sort of mimicked to be this GPS IIIF. And the impact, this is a precision orbit determination with, it gives you an error of a few centimeters. This error is larger than we see on other satellites that are, normally modeled. If you completely ignore the antenna, then the orbit determination error reaches decimeter level. So this is substantial and remains a concern. Next future GPS satellite we have to be aware of. Recently, the GPS, the US Space Force issued a request for proposal for GPS augmentation, they called resilient GPS. Previously, it was known as GPS-Lite. So it's the idea is to increase the resilience of GPS in general and to enhance the supply chain for GPS. This will be, they're looking for a supplier that will provide more than 20 additional GPS satellites, and the additional satellite will use a higher range of PRN. Those PRNs are still in the ICD, but they have never been used before. And the idea that the supplier will do things faster and cheaper. So these will not be conventional GPS satellite. They might have a high gain antenna that we don't know how it will be done. There will be different number of those satellites. They will vary over time. We probably will not know where they're pointing or what they're doing or the RF power. So, and it generally introduces a low-cost approach to the GPS satellite and increase our ability to model those satellites to the extent that we know their property even. So in summary, for NTS3, there's not much insight, not much geodesy that can be done from this single experimental spacecraft. We expect that the orbit determination will be challenging from the engineering perspective, but we will do it. And we will report as soon as we have interesting information from the side lobe, the new GNSS side lobe that we hope to survey with a sensitive receiver on board. Again, I'm highlighting the only real action item for this community here. Watch out from the data that will come at a certain point in time. We will let you know that it doesn't have this PRN for the satellite. For GPS IIIF, we expect the degraded modelability. And so we don't know anything about the antenna. The Space Force is not very good in releasing solar pressure data, as Galileo has done. So we need a concerted effort to get some information about the satellite, and then I'm sure the combined ingenuity in this community will work hard to figure out what the satellite is doing, but it's a challenge for this community. And finally, for resilient GPS, we need to wait for more information to figure out how to deal with that. Thank you.